students, welcome to Sunil's tutorial. I'm Sunil Milwani and today we'll be doing this chapter called as current electricity. Let's see what is a potentiometer. Let's see what is a potentiometer. Now, let's consider a long wire. Let's consider our long wire AB of uniform length L. Right? And let's assume that R is the resistance of the wire stretched on a board. Consider a long wire of length L and resistance R stretched on a wooden board. Right? Let us consider that you have connected a cell across the wire. This is the cell that's connected across the wire. Positive terminal, negative terminal. Now let's assume let's assume that VAB is the potential difference across the wire. Let VAB be the potential difference across the wire. Right? That means there is going to be a uniform fall of potential along the length of the wire. If that's the potential difference, that means the potential at one point is going to be greater than the other point, and as you move from one point to another point, the potential is going to fall. It is going to fall uniformly along the length of the wire. So I can say that there is a uniform fall of potential. There is a uniform fall of potential. There is a uniform fall of potential along the length L of the wire. Along the length L of the wire, right, from A to B. Now let's assume that let sigma be the resistance per unit length of the wire. The resistance per unit length of the wire. Let's assume that sigma is the resistance per unit length. Then I can say that the entire resistance is sigma into L. The entire resistance is going to be sigma into L. Right? Do we get this thing clear? Now, let's assume that I is the current flowing through the wire. Let I be current flowing through wire. Let's assume I is the current flowing through the wire. Then I can say that current is potential difference upon resistance. But resistance we just found out is nothing but sigma L. So VAB upon sigma L. Current is going to be VAB upon sigma L. Now let us consider, guys, can you see the figure again? Let us consider a point P on the wire such that length AP is L. Consider a point P on the wire such that its length is L. Let's assume L is the length of that part. Let R be the resistance. Let R be resistance of the wire AP. Therefore, I can say that R will be sigma into small l. Now let us assume that VAP is the potential difference between A and P. Let VAP the potential difference between A and P. In which case I can say that VAP will be nothing but IR, right? Potential difference is nothing but current into resistance. Now this can be written as current. We have already found out current as VAB upon sigma L, right? R we found out as sigma L. So in which case we will get this answer as VAB into L upon L, right? Now where I can say that VAB and L are constants, right? Hence I can say that VAP is directly proportional to L. VAP is directly proportional to L. Thus the potential difference between any two points of the wire, thus the potential difference between any 2 points of the wire, potential difference between any 2 points of the wire is directly proportional to the length of the wire, between these 2 points. Right? This is the principle of working of a potentiometer. Right? This is the principle of working of potentiometer. Right? Now one more thing what you need to know is that the fall of potential per unit length of the wire is called as potential gradient. The fall of potential per unit length, the fall of potential per unit length of the wire is called potential gradient. Fine. So do we understand the principal working of a potentiometer wire? Right? Do we understand the principal working of the potentiometer wire? Right. Now let's move on ahead. Now let's see how we construct a potentiometer wire. Right? Let's see the construction of a potentiometer wire. Construction of potentiometer wire. Right? Now let's see this. How do we construct a potentiometer wire? Now the potentiometer wire is a long wire which is of several meters. And it is stretched on a wooden board. See, I'll draw this and show to you. That's my potentiometer wire which has been stretched on a wooden board. This is my wire AB. Okay, and you have a battery of sufficiently large EMF which is connected between the two ends. A battery of sufficiently large EMF is connected between the two ends. You have a key connected here and you have a variable resistance connected to the other end, a rheostat, right? That's your construction of a potentiometer wire, right? So I can say that a potentiometer wire consists of several meters, long uniform wire, which is stretched on a wooden board, Fine. Now, a battery of sufficiently large EMF, a battery of sufficiently large EMF, that's about 4 to 6 volts, is connected between the two ends A and B, is connected between the two ends A and B of the wire, right? A variable resistance R, is connected in series with the potentiometer wire and the battery, is connected in series with the potentiometer wire and battery. Fine. Now, why do I need to have the potentiometer wire? It enables me to compare the EMF of two cells, right? Let's see one of the applications of this. How do I compare the EMF of two cells? Now there are two different methods to do that. I'll show you both the methods. Compare the EMF of two cells by using the cells separately. By using the cells separately. Now, guys, what I'm going to do is, instead of drawing the diagram again, I'm going to use the previous diagram only, right? Yes, can you just see this potentiometer wire diagram? I'm going to use this previous diagram only. That was my potentiometer wire. Now, the cell whose EMF has to be determined is connected to one end of the potentiometer wire, such that the positive terminal of the cell is connected with the positive terminal of the potentiometer wire, right? The other end of that cell is connected to a galvanometer, and the other end of the galvanometer is connected to a jockey which can move on the potentiometer wire, right? That's how current is moving. Right? So, do you understand how we find out the EMF of the cell? To find out the EMF of the cell, you connect the cell whose EMF has to be found out. Let's assume that the EMF of this cell is, say, E1. Right? The EMF, the positive terminal of the cell E1 is connected to one end of the potentiometer wire, which is that end of the potentiometer wire which is connected to the positive terminal. Okay? And the negative terminal is connected to a jockey through a galvanometer, and the jockey can then slide on wire AB, right? You slide the jockey along the length of the potentiometer wire in such a way that the galvanometer shows zero deflection. Keep sliding the jockey till the point the galvanometer shows zero deflection. Let us assume that the galvanometer shows zero deflection at point P, right? Now that means point P is the null point, right? Now let's assume that the length AP is say L1, right? That means I can say that the potential drop, I can find out the potential drop from A to P. The potential drop from A to P has to be directly proportional to length between A and P. That is the principle that is going to be used. Now I'll derive that and show it to you, right? So let us assume that E1 and E2 are be the EMF of the two cells, be the EMFs of the two cells, be the EMFs of the two cells, which are to be compared using a potentiometer, which are to be compared using a potentiometer. Right? Now, the positive terminal of cell E1, the positive terminal of cell E1 is connected to end A of the potentiometer wire, is connected to end A of potentiometer wire, is connected to end A of potentiometer wire at which the positive terminal of the battery is connected, which the positive terminal of the battery is connected. Fine. Now, the negative terminal of the cell E1 is connected to a jockey. The negative terminal of E1 is connected to a jockey, right? Is connected to a jockey through a galvanometer. Through a galvanometer. Now the jockey can slide along the potentiometer wire AB. The jockey can slide along the potentiometer wire AB. Fine. Now the jockey is slided along the length of the potentiometer wire and a point of contact P is found such that the galvanometer shows zero deflection. The jockey is slided along the potentiometer wire the jockey slided along the potentiometer wire and the point of contact P and the point of contact P is found in such a way that the galvanometer shows zero deflection. In such a way that the galvanometer shows zero deflection, right? Such that the galvanometer shows zero deflection. Now, such a point for which the galvanometer shows zero deflection is the null point. Now, let's assume that let L1 be the length of the potentiometer wire between A and P. Let L1 be length of potentiometer wire wire between A and P. Right? Now, since no current is flowing through the galvanometer potential at point P must be the same as the negative terminal of E1. Guys, one end of the galvanometer is connected to the negative terminal of the battery. Right? The other end is connected to point P. Now, if no current is flowing through the galvanometer, that means the negative terminal of E1 and point P should be at same potential. Only if they are at same potential, no current will flow. Had they been at different potential, there would have been potential difference and current would have flown through the galvanometer. So I can say since no current flows through the galvanometer, the potential at point P must be the same as the negative terminal of cell E1. Right? Therefore, I can say that E1 is nothing but the fall of potential. Guys, point P is at the same potential as the negative terminal of E1. That means the entire potential must have been used across the length AP. Right? So therefore, I can say that E1 is nothing but the fall of potential from A to P. Fall of potential from A to P. Right? That means this is nothing but the fall of potential along L1. Right? Fall of potential is nothing but current into resistance. Potential is nothing but current into resistance, which is current into resistance of L1. Right? Let us assume that I is the current flowing through the potentiometer wire and sigma is the resistance per unit length of the wire. Let I be the current flowing through the potentiometer wire and sigma be the resistance per unit length. Right? In which case I can therefore say that E1 therefore we said is current I, resistance of length L1 will be nothing but sigma L1. So it will be E1 will be equal to I sigma L1. Now replace the cell E1 by E2 and repeat the procedure. Right? I can say that replace cell E1 by E2. Replace cell E1 by E2 and the null point can be determined and the null point can be determined. I can determine the null point. Now, let's assume that L2 is the length of the potentiometer wire between A and the null point. Let L2 be length of potentiometer wire between A and null point. Therefore, I can say that E2 is nothing but I sigma L2, right? Now divide the two equations. If I divide the two equations, I'll get E1 upon E2 is nothing but I sigma L1 upon I sigma L2. So therefore I'll get E1 upon E2 is L1 upon L2. That's how I can compare the EMF of two cells by using I can compare the EMF of the two cells by using the two cells separately. Now I told you that there are two methods to compare the EMF of the two cells. Here I was using the two cells separately. There is another method to compare the EMF of two cells, and that is called as the sum and the difference method. Compare EMF of two cells using sum and difference method. Using sum and difference method. Now, I'm not drawing the potentiometer wire again. Now I'll just show you that how we do this. Now in this method, instead of using the two cells separately, the two cells are connected in such a manner either to assist each other or to negate each other. So I could connect the two cells where I've connected E1 in the potentiometer wire. I could have connected E1 and E2 in this manner. This is E1 and this is E2. Positive, negative, positive, negative. This could have been one method where they would assist each other, or I could connect the two cells in such a manner that E1 and E2. This is E1, this is E2. Positive, negative, negative, positive, such that they oppose each other. Right? So in the potentiometer wire, guys, let's have a look at the potentiometer wire. Here, instead of connecting that E1, I could have connected E1 and E2 in such a manner that they either assist each other or they oppose each other. Fine, do we get this thing here? So I can say that in this method, instead of using the two cells separately, both the cells are connected in such a manner that they either assist each other, both the cells are connected in such a manner that they either assist each other and their total EMF is E1 plus E2, or now in the first case I'm going to connect them that they assist each other. Now the positive terminal of the combination is then connected to terminal A. The positive terminal of the combination is connected to terminal A. The positive terminal of the combination is connected to terminal A, where the positive terminal of the battery is connected. The positive terminal of the battery is connected. Fine. and the negative terminal of the combination is connected to a jockey through a galvanometer. The negative terminal of the battery is connected to a jockey through a galvanometer, right? The null point is determined as the jockey is slided on the wire, and null point is determined right. Let us assume that L1 is the length of the potentiometer wire between A and the null point. Let us assume that L1 the length of the wire between A and length of the wire between A and the null point. So in which case I could therefore say that E1 plus E2 is I times sigma L1, right? So this is when they were assisting each other. Now the cells are connected in such a way that they oppose each other. The cells are connected in such a way that they oppose each other, right? Now the combined EMF of the cell in that case would be E1 minus E2. The combined EMF of the cell then would be E1 minus E2, right? The null point is determined. Null point is determined by sliding the jockey on the wire. Once I slide the jockey on the wire, I'll come to know my null point. Now, let's assume that L2 is the balancing length of the potentiometer wire for the null point. Let L2 be the balancing length of the potentiometer wire let L2 be the balancing length of the potentiometer wire for the null point in the arrangement, in which case I can therefore say that E1 minus E2 is I times sigma L2, right? Now if I divide the two equations, I'll get E1 plus E2 upon E1 minus E2 is nothing but I times sigma L1 upon I times sigma L2, right? I and sigma gets cancelled. Now if I apply componendo and dividendo, I'll get E1 upon E2 I'll be able to say that E1 upon E2 is L1 plus L2 upon L1 minus L2. Fine. So that's how you will be able to determine the EMF or compare the EMF of two cells by using the sum and the difference method. Right? Now what are the precautions to be taken? Now, while performing the experiment on potentiometer, the following precautions have to be taken. The EMF of the battery must always be greater than the EMF to be compared, right? So that's the first precaution to be taken. Second, the positive terminal of E1 and E2 must always be connected to the positive terminal of the battery of the potentiometer wire. So two precautions to be taken. One, the EMF of the battery must be greater. The EMF of the battery must be greater than the EMF to be compared. Right? That means if I am using the sum and the difference method, the EMF of the battery must be greater than E1 plus E2. Fine, do we get this thing here? Second, the positive terminal of the battery must be connected to the positive terminal of cell E1 and E2. Right? So these are the two precautions to be taken while you're doing when you're using a potentiometer wire. What are the advantages of using a potentiometer wire? What are the advantages of using a potentiometer wire? By increasing the length of the potentiometer wire, the fall in potential per unit length of the potentiometer wire, that is your potential gradient, will be very small. Hence, a potentiometer wire is used for measurement of very small potential difference accurately. Right? A voltmeter cannot measure a very small potential difference, but a very small potential difference can be accurately measured by using a potentiometer wire. Fine, do we get this thing here? So that is your advantage of using your potentiometer wire. By increasing the length of the potentiometer wire, the potential gradient can be made as small as possible. The potential gradient can be made as small as possible. The potential gradient can be made as small as possible, and therefore the potentiometer wire can be, or potentiometer can be used to measure very small potential difference accurately. Hence, potentiometer can be used to measure small potential difference very accurately. Right? Okay. So do you understand this? Now, how do I find out the internal resistance of a cell? Right? Let's see how can I find out the internal resistance of a cell. Let's see the determination of internal resistance of cell. let's see how can we find out the internal resistance of the cell. First thing I need is a potentiometer wire. That's my potentiometer wire. This is terminal A, this is terminal B. Potentiometer wire is connected to a battery which is then connected to a key, which is then connected to a rheostat. A rheostat is a variable resistance. Okay. Now you will connect a battery to the positive terminal, the other end of which the negative terminal is connected to a jockey through a galvanometer, and let's connect a resistance box and a key here. Right? Let's call this key as, say, key 2, K2. This is my positive and negative terminal of the battery of the cell whose internal resistance has to be determined. Fine. Let's assume that the null point is found at point P. Okay. Now, let's see this. The battery, let's assume that battery C is connected. Battery C is connected to cell E, whose internal resistance has to be determined. Connected to cell E, whose internal resistance has to be determined. Now, such that C is much greater than E, right? Okay, let's move on ahead. Now I can say that a key K1 and a rheostat is connected in series with the potentiometer wire. K1 and rheostat are connected in series with the potentiometer wire. Are connected in series with the potentiometer wire. Now, the positive terminal of the cell is connected to end A. The positive terminal of cell E is connected to terminal A. Of the potentiometer wire, and positive terminal of the positive terminal of the cell E is connected to the terminal A of the potentiometer wire, which is connected to the positive terminal of the battery, which is connected to the positive terminal of the battery. Fine, do we get this in here? Right, now let's move on ahead. The negative terminal of cell E is connected to a jockey through a galvanometer. The negative terminal of cell is connected to a jockey through a galvanometer, right? Now, a known variable resistance, that is your resistance box and key 2 are connected across the cell. A resistance box R and key K2 are connected across the cell. Fine. Now initially K2 is kept open so that the resistance R remains outside the circuit. Initially K2 is kept open so that resistance R remains out of the circuit. Right? Now, current is sent through a potentiometer wire by closing key 1, key K1. Current is sent through the potentiometer wire by closing key K1. Fine. Now, as soon as I close key K1, there is going to be a potential drop that will be produced along the length of the wire, which produces a potential drop across the length of the wire. Fine. Now, the jockey is then touched at different points of the wire, and the point of contact for which the galvanometer shows zero deflection is determined. So, using the jockey null point is determined. Right? Once I get the null point is determined. Length L1 between the null point and end A is measured. Length L1 between the null point and point A is measured. Right? Now, once you have this, now since no current is passing through the cell, in this case, the fall of potential along L1 represents the EMF of the cell. Since galvanometer shows zero deflection, therefore I can say that point P and negative terminal of the cell are at same potential, right? Which means that the fall of potential along length L1, therefore fall of potential along length L1 represents the EMF of the cell, represents EMF of cell. Sorry. Now, a suitable resistance is taken from the resistance box by unplugging the key and closing unplugging the key and by closing key K2, and again the null point is determined. A suitable resistance is taken from the resistance box. A suitable resistance is taken from the resistance box and key K2 is closed. Right? Once I close key K2, the null point is again determined in the same manner. The null point is determined again in the same manner. Right? Once I get the null point again, in this case, since the current is flowing through the cell, in the previous case, since the potential at the negative terminal of the cell and at point P was same, therefore there was no current flowing through the cell. Here current is flowing through the cell. Now if current flows through the cell, I can say that in this case current flows through the cell, right? Hence the fall of potential along L2, hence the fall of potential, hence the fall of potential along L2 is equal to the terminal potential difference, terminal potential difference, right? Therefore I can say that E upon V will be nothing but L1 upon L2, right? Now if current I is flowing through the circuit, let I be the current flowing through resistance R and R, be the current flowing through resistance R and internal resistance R. Then I can say by Ohm's law, I is equal to E upon R plus R, right? So in which case I can say that I have the value of I can say also I is equal to V upon R, also I is equal to V upon R, right? Now if I divide the two equations, I can say that in both the cases I is same. I can say from the above two equations, you could say that E upon R plus R is equal to V upon R. Therefore I can say that E upon V cross multiply is R plus R upon R, right? But E upon V we found out is L1 upon L2, but E upon V is L1 upon L2. Therefore I can say L1 upon L2 is R plus R upon R, right? Now in which case I can therefore say that if I simplify this, I'll get R is L1 minus L2 upon L2 into R. That's how you find out the internal resistance of a cell. Fine, do we get this thing clear? Next, what do we understand by thermoelectricity? What is thermoelectricity? Now, thermoelectricity is nothing but the arrangement of two metallic wires joined end to end. What will be the advantage of joining two metallic wires end to end? Guys, see this. Suppose if I have two metallic wires joined end to end, right? this is iron and this is copper, right? They are joined end to end, right? Now such an arrangement is called as thermocouple. Now when you have two wires of different material joined end to end, a potential difference is developed between the two junctions when they are kept at different temperatures. So if the two ends are kept at different temperatures, there will be a potential developed here and there will be a potential developed here. There will be a potential developed at the two junctions, and this potential that is developed is called as thermoelectricity, right? So if I have two metallic wires of different material joined end to end, and if the junctions are kept at different temperature, that would develop a potential at the junctions, and that potential would be called as thermoelectricity. Fine, do we get this thing clear? I can say that the arrangement consisting of two metallic wires joined end to end is called thermocouple. Fine. Now a potential difference is developed between these two junctions. A potential difference is developed between these two junctions. A potential difference is developed between these two junctions when they are kept at different temperatures. When they are kept at different temperatures. Fine. When they are kept at different temperatures. Now, this potential difference is called as thermo EMF. This potential difference is called thermo EMF, and the electric current developed in this is called as thermoelectric current, and the electric current developed is called thermoelectricity or thermocurrent. Thermoelectricity. Fine, do we get this in here? Question: how can I have electricity generated just by connecting two wires of different material? Let's see how this actually works. These are two wires of different material joined end to end. Let's assume that this is the iron wire, this is copper wire. Fine. Now, let's try to understand this. The free electrons that are present in a conductor per unit volume is called as the electron density. Right? Free electrons, we'll start right from the basics. Free electrons present in a conductor per unit volume is called as electron density. Fine, do we get this in here? Now, the electron density increases with the increase in the temperature of the conductor. Electron density increases with increase in temperature. Right? Now, when a thermocouple is welded the two ends of the metallic wire of different, when a thermocouple is formed, welding the ends of two metallic wires of different metals, the electrons from metal having greater electron density diffuse into the other metal having too low electron density. If I have two different metallic wires, obviously the electron densities will be different. If I fuse together the two wires by welding them, electrons from the metal having higher electron density will fuse into the material having low electron density. So I can say when thermocouple is formed, when thermocouple is formed by welding the ends of two metallic wire, the ends of two metallic wires, by welding the ends of two metallic wires of different metal, right? The electrons from metals having greater electron density, the electrons from metals having greater electron density diffuse into the other metal having low electron density, diffuse into the other metal having low electron density. Right? Now, this, since you have electrons diffusing from one metal to another metal, that means there is a movement of charge. If there is a movement of charge, that means there is going to be a small potential that will be created. There is different electron density on either side of the welded region. So obviously, if there is different electron density, there is different amount of charge on two sides. There is different amount of charge on two sides. Hence, a small potential is going to be developed. Right? Now, this produces a small potential difference across the junction. This produces a small potential difference across the junction. This produces a small potential difference across the junction of the two metals. Called as the contact potential. Called contact potential. Fine. Now, once I have the contact potential, I can say that the value of the contact potential depends upon the temperature of the junction, because we said that electron density depends upon the temperature. Right in the beginning, I said that electron density increases with the increase in temperature. If the electron density changes, obviously the potential difference that is developed across the junction will change. So I can say that the value of contact potential, depends upon the temperature of the junction. Fine. Depends upon the temperature of the junction. If the two junctions are at same temperature, the contact potential of the two junctions are same, and hence the two junctions tend to send equal amount of current in opposite directions. Right? If the two junctions are at same temperature, meaning, guys, can you just please look up at the diagram? This is one junction, this is the other junction. If the two junctions are at same temperature, there's going to be some potential difference developed here, there's going to be some potential difference developed at junction number 2. Due to the potential difference, due to the contact potential, some current is going to flow at junction 1. Since the other junction is also at the same temperature, same amount of current will flow through the other junction also, right? So if the two junctions are at same temperature, the contact potential of the two junctions are same. The contact potential of the two junctions are same. The contact potential of the two junctions are same. As a result, hence the two junctions tend to send equal currents in opposite direction. Hence, the two junctions send equal currents in opposite directions. Right? Since equal amount of currents are sent in opposite direction, there is no current through the thermocouple. As a result, there is no current through the thermocouple. As a result, there is no current through the thermocouple. Right? Now, if one of the junction is heated, there will be greater diffusion of electrons at the hot junction than at the cold junction. If one of the junctions is heated, then if one of the junction is heated, then there is greater diffusion of electrons. There is greater diffusion of electrons. There is greater diffusion of electrons. There is greater diffusion of electrons at the hot junction than at the cold junction. At the hot junction than at the cold junction. Right? Now, hence the contact potential at the hot junction becomes more than that of the cold junction. If there is greater diffusion, obviously the contact potential will increase. Hence, the contact potential at the hot junction becomes more than that at the cold junction. Right? This produces a net EMF between the two junctions if the contact potential changes. This produces a net EMF between two junctions, which is called as the thermo EMF. As thermo EMF, right? Resulting in a current which is thermoelectric current. Resulting in a current called thermoelectric current. Right? That's the reason why you have current flowing through. That's the reason why you have current flowing through when you have two different materials joined at two different junctions. This conversion of heat energy into electric energy by using a thermocouple is called as thermoelectricity. This conversion of heat energy into electric energy by using thermocouple is called thermoelectricity. Fine, do we get this in here? So do you understand the concept of thermoelectricity? Okay, we'll stop this here for the day. Thank you very much.